Hi, in this lecture we will solve a problem using the method of sections for the analysis of trusses. I'm going to draw the truss that has to be analyzed. The horizontal member at the top chord as it's called, the bottom chord, and the vertical members, and also 3 diagonal members. And then this truss is supported by a pin and by a roller at its left end. And the joints are labeled A, B, C, D, E, F, G, and H. The panel dimensions for the truss are 2.4 meters each. Member DE at the right end of the truss is 2 meters tall, and member AH at the left end of the truss is 5 meters. And this truss has one single force having a magnitude of 6 kilonewtons oriented vertically and downwards, acting at joint D. We are asked to determine the following. Firstly, whether in this truss there are any zero force members for this specific loading configuration. This, as I mentioned before, is a very important point in the analysis of a truss, that is looking for zero force members. This is the first fundamental step in any problems involving the analysis of a truss, looking for zero force members. And that's what the first question asks. The second question asks to determine the force in members A, B, BG, and FG. And more importantly is also that we have to solve for each force from an equation that contains only one of these three required member forces in that equation. So in one equation, only member or the force in member AFB should show up. In another one, only the force in member BG, and in another one, only the force in member FG should show up. So let's start with point 1. If you look at joint D, you can hopefully easily identify a T configuration of that joint, meaning that the 6 kilonewton force lines up with member DE. So the force in D equals to the applied force, 6 kilonewtons in compression, and member CD is a zero force member, because at point D, no other forces act except for these three. Going on now to the second question, since there are no other zero force members in the truss except for member CD, then that statement means that we must eliminate the other two member forces when we solve for the third one. And eliminating unknowns or other member forces can only be done by writing moment equations. So in this case, because for each equation we have to eliminate the other two member forces, it means that we have to write 3 moment equations. We cannot write force summation equations in this question because we are asked to eliminate the other unknowns. So I've highlighted members A, B, BG, and FG here in light blue, and section XX cuts through all these 3 members and cuts all the way through the truss, so we can separate the truss. And hopefully you have recognized that this is a cantilever truss, and if we start analyzing from the truss from its right end, or in this case for the method of section, we analyze the right hand side free body diagram, then we don't need to calculate the reaction forces at A and H. We just begin from the right to analyze the member forces. So let's do so and start by effectively cutting the truss along XX, and then we will draw both of the resulting free body diagrams. So you always have to draw both free body diagrams, then look at them, and then decide which one you will analyze. In this case, we know, because it's cantilever truss, we know that we will analyze the right-hand side of the free body diagram, but regardless, we will draw both of them. So, left-hand side, right-hand side, have to make sure we draw them with a cut through the correct members, like so. You can see the three members that are cut now on the left-hand side free body diagram. And now let's complete the right-hand side free body diagram, again with the three members that we've cut there as well. Labeling the joints, so we know which joint is which joint. The externally applied force at joint D, 6 kilonewtons vertically downwards. The external reaction forces at A, AX and AY, replacing the pin support, and at H, HX, horizontally replacing the roller. We, of course, have to show the dimensions, the 2.4 meters, the panel sizes. All of them are 2.4 meters. And now we're just drawing the internal forces. We assume direction that we think would be the right ones, the correct ones. So FAB in tension maybe. FBG also probably in tension. And the third one, which is FFG in, say, compression. So again, arrows pushing into the joint. Joints represent compression. Arrows pulling away from the joints represent tension. Well, let's see what equations we need to write in order to solve for the three unknowns. But then again, let's mention what I've said before, that because this is a cantilever truss and we have no desire, we don't need to solve for the reaction forces at A and H. We will then we have no choice then to use the right-hand side of the free body diagram. And this is what we will use. Now, in order to eliminate two forces, we have to find where these two forces intersect. And for example, if we sum the moments at point G equals to 0, this is point G, joint G, we have two forces intersect, FGF and FBG at G, so we can solve for the force in member AB. You can also notice that FAB and FFG intersect somewhere off the body, all the way here to the right at point, let's call it I. And if we sum the moments at point I equals to 0, then this equation will solve for the force in member BG. Now, we need to determine the location of point I, so we know that AH was 5 meters, DE is 2 meters. By similar triangles, we can easily, even by inspection actually, determine that member BG is 4 meters long and member CF is 3 meters long. And also by similar triangles, we can determine that point I, joint I, is 2 panels away, 4.8 meters away to the right of joint D. So finally, sum of the moments at B, where FAB and FBG intersect, will right away solve for the force in member FG. So you can see very easily, very simply, we can write three equations, three moment equations, and each of them will have one single unknown. Let's start with the summation of moments at G. And this is a very simple equation. one single unknown, FAB, and if we calculate, FAB will be equal to 7.2 kilonewtons in tension. Our assumption was correct. The member is in tension. Summing the moments now at point I to the right of the truss, we know these dimensions, we know the location of point I, so another simple equation as you can see on the screen. And the result for the force in member BG is now negative 3 kilonewtons, or 3 kilonewtons in compression, because our original assumption that the member would be in tension was incorrect. So we can actually indicate that with these green arrows on the diagram, like so, in order to remind us that the member is actually in compression, not in tension. Finally, the third equation, sum of the moments at point B equal to 0, FGF times its moment arm with regard to point B. So this is the moment arm here on the diagram, the perpendicular distance from B to FG, like so. Well, we'll have to determine what this moment arm is, so it's a little geometry here that we need to deal with. You can recognize angle theta at I and at F, and then angle theta at B by BG and distance D being perpendicular to BC and FG respectively. So therefore D will be equal to BG cos theta. BG is 4 meters long, and cos theta from the big triangle AIH is equals to AI, which is 12 meters, divided by HI, which we can calculate it easily by applying Pythagoras in this big triangle AIH. And BG cos theta gives us a number 3.69231 meters. I kept better precision so we don't lose accuracy in the end. And finally, FGF can be determined and equal to 7.2 kilonewtons, also in compression. So hence we have solved for all the three unknown member forces by writing three moment equations with a big advantage that each equation had one single unknown. Very easy, very practical to use. Thank you very much for attending this lecture, and I will see you at the next one.